Okay, now we're starting engineering math A, a different course, and the first subject is the Laplace transform. Here's my little, here we go. This integral here, this definite integral, is the Laplace transform. Technically, it's the unilateral Laplace transform. If you've ever heard of a bilateral Laplace transform, the lower limit is minus infinity. We're not covering that. So this is what we mean by the Laplace transform. It's something, it transforms a function of t. Sometimes I'll call that time domain. And it means put that function in this integral like this, and then evaluate the integral. You'll see that if you integrate over t, you integrate all the t out of it, and you're left with a function of s. So the Laplace transform is a function of s, this potentially complex number. So this is the notation for the Laplace transform. It's an operator on a function. This is the operation. Here's the output. The notation convention is lowercase for the time function or t function, and uppercase for the Laplace domain function. So you can say that I can take the inverse Laplace transform of this function on the right, and it will give me the original f of t. We call that a Laplace transform pair. See this little negative sign on the lower limit? Usually that, you can ignore that. What it really means is the limit at 0 from the left. And if your function doesn't contain an impulse or a direct delta function at 0, then it doesn't matter. You could just call this plain old 0. But if it does contain a direct function at 0, this limit is just to the left of it, so that the integral will actually include that direct delta function. I'll talk about that subtlety later in the course. Not all functions have a Laplace transform. And this integral, even if it does have a Laplace transform, the integral will only converge for some certain s's, where the real part of s is greater than some constant. I already talked about this lower limit. We're actually not going to evaluate this integral all that much. You'll see it leads to a table of transforms and properties, and mostly we're just going to use the table. At this very beginning, we'll use this integral definition to discover some transform pairs and transform properties. We're not going to put that much emphasis on actually taking this integral. Generally, we're only interested in functions that are 0 for t less than 0. We can usually assume that because it's going to get lopped off here anyway. The integral starts at 0. So no matter what it is below 0, it doesn't matter to the Laplace transform. So that's what it is. So let's try one. What about where the function is just 1? Could be 1, or it could be the unit step. And we'll talk more about the unit step later. Here's what it means. So let's take that integral. Put 1 in that definition. F of t is just 1, and you're just taking this in. Okay, you integrate e to the minus st. It is this. We evaluate it between those limits. That means take the limit at each limit of the integral. So this top limit says take the limit as t, our variable of integration, goes to positive infinity. The lower limit says take the limit as t goes to 0 from the left. Well, this lower limit, let's see, when t equals 0, okay, that's a 1 on top. So we get that. What about this upper limit? T goes to infinity. Well, if s were negative, this limit wouldn't exist. It would go off to infinity. But if s is, or at least the real part of s is greater than 0, then this top part goes to 0. This whole thing just evaluates to 1 over s. We have a restriction on what s can be. So for the Laplace integral to exist, we required the real part of s to be greater than 0. That's not a problem. And the Laplace transform of 1, the constant 1, is just 1 over s. So now we have a Laplace transform pair. Time function on the left, the Laplace domain equivalent on the right. And actually this would hold for any function that's 1 for time t greater than 0. It really doesn't matter what it is for time t less than 0, because that's not part of the integral. So that's why it works for the unit step. But it could work for anything that's, as long as it's strictly 1 t greater than 0. Okay, let's look at what about this thing? You multiply any function by e to the at, and then we'll look at e to the at itself. So let's put this in the definition. That means that we can add the exponents when we multiply these e's. We have that. And if you look at this, it is the Laplace transform where we use s minus a instead of s. Means this, so if we already had the Laplace transform of f, we could find the Laplace transform of e to the at times that f by just using the same Laplace transform but evaluating it at s minus a instead of s. So what if we do that? So how can we find the Laplace transform of e to the at then? Well, e to the at is e to the at times 1. We just found the Laplace transform of 1. We now evaluate it at s minus a instead of s. That means 1 over s evaluated at s equals s minus a. That means this. 1 over s minus a. That's the Laplace transform of e to the at. And because this guy needed the real part of s to be greater than 0, we now require the real part of s minus a to be greater than 0, or the real part of s greater than a. I'll try to get through this. This one's a little bit tougher. What's the Laplace transform of t to the alpha, where alpha doesn't have to be an integer? Laplace transform of t to the alpha means this integral. Let's look at that integral. First, we'll do a variable substitution. We'll call u equals this st. This gives us the variable substitution. We got to do that on the limits as well. And that upper limit will go to infinity as long as s is greater than 0. Now we have a restriction on s. Here's what will become. Pull out the s stuff, and we have this integral. I can change the u's to t's, it doesn't matter. Variable of integration, we're going to integrate it out anyway. So I'll write it using it. Doesn't look like we got very far. This is still, how do you take this integral? Well, it turns out it's a gamma function. Here's what the gamma function is. It's described as a function of x, say. It is this integral. And we're not going to worry too much about it. It's only defined for x greater than 0. That's what we call the gamma function. So that this integral up here is actually the gamma function with the argument alpha plus 1. Our alpha equals x minus 1. So we require alpha to be greater than minus 1. That came from this restriction of the gamma function. So here is our Laplace transform pair. The Laplace transform of t to the alpha is this gamma function over s to the alpha plus 1. We require that s be greater than 0, or actually the real part of s greater than 0, and the alpha part is greater than -1. Don't worry about evaluating the gamma function. We'll not be taking this integral. At best, we'd use some table for the gamma functions. Let's look at just a couple of them. So here's the Laplace transform of t to the alpha again. Take my word for it that the gamma function with the argument of a half is the square root of pi. And the gamma function has this relationship. If I add 1 to the argument, it's multiplying by x. So the Laplace transform of t to the -1/2, this, just using this formula up here, and that numerator is the square root of pi. So there's the Laplace transform of t to the -1/2. T to the half, it's this. This gamma of 3/2 by this relationship is 1/2 the gamma of 1/2. That was the square root of pi. Have this result. So we have 2 more Laplace transform pairs to put in a table. Here's the time function. Here's the Laplace transform. Here's the time function. Here's the Laplace transform. What about when that exponent is an integer, or at least one greater than 0? Well, here's another property of the gamma function. In fact, the gamma function is a generalization of a factorial. Gamma function can have non-integer arguments, but for integer arguments, you get this relationship. It is a factorial. So if we're talking t to the n, where n is an integer, this Laplace transform is this. That numerator is now n factorial. So we have all the Laplace transforms of all the t to the n's. So here's the first few. If n were 0, we're back to 1, and we already did that one. That's 1 over f. If n is 1, Laplace transform of t, it's 1 over s squared. And t squared is 2 over s cubed. T cubed is 6, which is 3 factorial over 4. So see that the power of s in the denominator is 1 more than the power of t in the times functions. I'll go over some of this in a subsequent recording. I'll stop there. This is the first recording and first lesson of Engineering Math A.